Okay, good morning, everyone. I still see a few persons trying to join the classroom, so I'll wait a few more minutes before I begin. Okay, good morning again, everyone. I still see a few persons joining or trying to get on. Dr. Brown is also on, Dr. Inka Brown. Okay, so as the lecture goes along, we will try our best to answer the questions in the chat room as much as we can, and whatever concerns you may have. Okay, let's get started. So as I mentioned last week, this week's lecture, we'll be reviewing Wittig reactions, and we're moving on to the reactions of carbonyls as nucleophiles. Earlier, students have been asking about the course test. You'll be informed in a few days as to the date, time, and format of the course test. Just to note that the test will cover all that you'd have learned since the first course test up to today's lecture. So basically, the course test will cover Grignard reagents and the reactions of carbonyl compounds. So everything that you'd have learned since the first course test and what we'll cover, up to what we cover today, will be on your course test number 2. And we should have some information about the format and so on in the coming days. All right, so let's get started. Okay, so we're looking at Wittig reactions, and we did this the last lecture before we had the break. So we just thought we just review it briefly before we move on to the other topic on the carbonyl compounds. So what is a Wittig reaction? It's a reaction between a carbonyl compound and alkyl halide, and we are making a carbon-carbon double bond. And we can predict the product of the reaction basically by looking at the carbon, the carbonyl group is attached, carbon number 2 here, and the carbon which bears the alkyl halide. And this is where your new bond is generated. So if we look at our ketone here and our alkyl halide, let me deactivate the notations. Give me a minute. Settings, notification settings. Okay. All right, so let me deactivate the settings. Okay, so it is a reaction in which the double bond is formed between the carbon which bears the carbonyl group, which is carbon 2 in the structure, and the carbon bearing the alkyl halide, which is carbon A in the structure. At the end of the reaction, we are forming a carbon-carbon double bond. And so you can actually predict the product by just erasing the oxygen and removing the halide and connecting these two carbons, and that will give us our Wittig product. So let's look at how the mechanism of the reaction occurs. So the first step normally involves generating the yelide, and now we start an alkyl halide, which we convert to a phosphonium salt. In the presence of a base, we create the yelide, and then the yelide reacts with a carbonyl compound to give double bond. So let's look at an example of the reaction mechanism. The first step is generation of our yelide. So we start with triphenylphosphine, and normally we represent the 3 phenyl groups using pH, and please note it is capital P, common H. So we normally represent the phosphorus with the 3 aromatic rings as P with our pH groups. It's an abbreviated way of depicting the triphenylphosphine. So the substitution reaction is going to occur, and so we are going to be reacting our triphenylphosphine with our alkyl halide, and we're going to be replacing the bromine. So here our nucleophile is going to be the phosphorus with its lone pairs, and we're going to be doing a substitution reaction which replaces our bromine. As I mentioned before, the pH groups here represents 3 benzene rings, and please note that we abbreviate the phenyl with a capital P and a common H. All right, so let's look at what happens. So I need to draw an arrow to show how the triphenylphosphine is going to react with the alkyl halide. Which direction do I draw the arrow? Anybody? In the chat room, anyone?
From the
Okay, 2. Go ahead. Go ahead. Okay, great. So we are
from the lone
losing the lone
pairs
pair
from
electrons
the lone pair.
to the carbon, which is delta positive, correct. So here, this is our nucleophile, and the carbon positive charge will become our electrophile. So we draw the arrow from the triphenylphosphine, the phosphorus lone pairs to the carbon. Great. And so we have the loss of the bromine. Can someone tell me what kind of reaction is taking place here? Very good, SN2. Justin, why couldn't it not be SN1? Remember, SN1 goes via carbocation. SN2 is concerted. As the nucleophile is coming in, the halide leaves at the same time. Great. So the first step is we are replacing or substituting our bromine with our phosphorus, and we end up with our phosphonium salt. The next step involves the reaction of the phosphonium salt with a base. So notice that because phosphorus has given up its lone pair electrons to form this new sigma bond, the phosphorus now becomes positively charged. So the plus charge on the phosphorus. And we have our counter ion, which is the bromine, which was lost. The next step is the formation of our ylide. And so we are going to react our phosphonium salt with a base. And if you look at this structure in the box, you'll see some arrows, and these are showing the inductive effect. So the positive charge on the phosphorus is going to result in a weakening of the CH bond, which makes it easy. These protons can be easily lost in the presence of a base. So because electron density is being pulled towards the phosphorus, it makes these protons more acidic, and so a base will be able to remove either of these protons. So again, how do I draw my arrows to show the base removing one of the protons? How many arrows do I need to draw? Anybody?
2 arrows, one going from the CH bond to the central carbon, and one from the oxygen to the hydrogen.
Wonderful, great. So we have 2 arrows. We have the base abstracting this proton, and the electrons are going to go onto the carbon. So now the carbon becomes negatively charged, whereas the phosphorus is positively charged. And so we can actually depict the ylide in 2 ways. We can actually depict the ylide showing the separation of charge, or you can actually show it double bond between the carbon and the phosphorus. So it has a resonance form, and this is known as phosphorine. So this ylide will now become the reactive species, which reacts with our carbonyl in the Wittig reaction. So here we have the resonance form. So where the electron of the carbon will go in to replace the lone pairs on the phosphorus, we end up with the resonance form, the carbon-phosphorus double bond. So this ylide now will react with our carbonyl compound. So here we have our carbonyl, and an easy way, or one way to do or to show the mechanism is to align the structure so that the nucleophilic carbon can attack the electrophilic carbon. That is, the carbon from the ylide directly above or close to the carbon of the carbonyl compound. This is our nucleophilic carbon, and this is our electrophilic carbon. That way we can, once we align the structures, we can easily form the four-membered ring intermediates. So, my arrows, anybody? How will I draw my arrows? From orange C to blue C. Thank you, Michaela. So we draw an arrow from the nucleophilic carbon to the electrophilic carbon. Great. And notice that this reaction also involves the electrons from the bond, oxygen, going to form a new bond between the oxygen and the phosphorus. So at the end of this reaction, what we have is a four-membered ring. So we have a carbon-carbon bond being formed and an oxygen-phosphorus bond being formed. So the negative oxygen will take away electrons from the carbon, and we'll use those electrons to form a bond with the phosphorus. So we have the formation of a phosphorus oxygen double bond and a carbon-carbon double bond. So we are breaking the carbon-phosphorus bond to form a carbon-carbon double bond, and we are breaking the carbon-oxygen bond to form a phosphor-oxygen double bond. And this reaction occurs simultaneously, or these bonds are being broken and formed simultaneously. So at the end of the reaction, we end up with a carbon-carbon double bond, and we have our triphenyl phosphine oxide or byproducts. Are there any questions? So as Dr. Brown has said in the chat room, it is very important that we, yes, Shanae, go ahead.
Miss, I think I was lost. Where did the carbonyl group come from? The carbonyl.
That's another reactant.
Oh, okay.
This carbon you're referring to, another product. So we are adding the ylide to a carbon. It's a reaction of carbonyl groups. So we first form the ylide, and we are reacting the ylide with a carbonyl group. So the ylide is acting as a nucleophile. Remember, carbonyls undergo nucleophilic addition reactions. So the ylide is acting as a nucleophile, it's reacting with a carbonyl group. Yes, Kalisa, go ahead. Or Casella, I'm sorry, I mispronounced your name.
Hi, Miss, good afternoon.
Good afternoon there.
Can you explain the resonance that is taking place? I don't understand why they break off and form double bonds. Here.
Which here?
Here, Miss.
Here.
Yes.
Okay,
miss.
so you have a four-membered ring. Let me see if I can go back. I'll go back without the arrow. Okay, so we have a four-membered ring here. Correct?
Yes, Miss.
There are only two ways the arrows can go. If the arrow, if this bond breaks, are you following?
Mm-hmm.
If the
Yes, I'm following.
If the oxygen phosphorus bond breaks and the electrons go in to the carbon, and the carbon-carbon bond breaks and it goes into the phosphorus, we are reforming our reactants.
Oh.
Oh.
Okay.
However, if the carbon-oxygen bond breaks and the electrons go in, and the phosphorus carbon bond breaks, and the oxygen carbon bond breaks, and these electrons go in, then we will form our alkene and a phosphorus oxygen double bond. So if you follow the direction of the arrows, there's only one way to get your product. If you go the other direction, you're going to reform your starting reagents. Make sense?
Miss. Thanks, Miss.
Okay. Okay. So part of reaction mechanism is being able to follow the arrow movements and what happened as a result after the bonds have shifted. So the arrow is indicating that 2 electrons are moving and you're breaking the bond. So those 2 electrons are now going here. So you're forming a new phosphorus oxygen double bond. If you use this arrow, you're saying that electrons here are moving to form a new bond between the carbon and the carbon. So you're breaking the carbon phosphorus bond, and you're also breaking the carbon oxygen bond. So at the end of the reaction, we have formed a new bond between the carbon and the carbon here. An alkene is formed, and our byproduct is the triphenyl phosphate oxide. Okay? Any questions? Should the CH2 anilide be a CH3? Remember that when we were forming the ylide, the first reaction was the triphenyl phosphine alkyl halide, where the phosphorus was positive and the carbon had 2 hydrogens. Oh, you're referring to here? Yes, correct. Yes, you're correct. It's an error. This should have a CH3. Thank you for pointing that out. Anake, Miss, you were saying something. If we didn't, we would form back. I was pointing out that the arrow placement is important, or how you draw the arrows in the 4-membered ring is very important. Because if your arrows you had, let me go back. Let me go back. And let me use. If after forming the 4-membered ring, you drew the arrows this way, in a sense, what you're doing is reforming the products, because this would reform your ketone, and here you'd have been reforming the ylide. So I was making the point that your arrows, the direction of your arrows are important. They mean something. It's not arbitrary. This arrow here is indicating that you're breaking the phosphorus oxygen bond, electrons going in, and a new bond is being formed here. This is indicating that you're breaking the carbon-carbon bond, electrons are going in, and a new bond is being formed between the carbon and the phosphorus. So if the arrows were drawn like this, you're reforming your starting material. As I was making the point that you need to be careful how you draw the arrows, because they mean something. It's not arbitrary. Clearer? Anake? Okay, so that's the Wittig reaction. So in summary, the Wittig reaction converts a carbonyl to a carbon double bond, and it's a reaction between a carbonyl and a ylide, which we generate from an alkyl halide. And this reaction, the carbonyl is the electrophile, and the ylide is the nucleophile. And so you should be able to work out any product of a Wittig reaction, and you need to be able to reproduce the mechanism of the Wittig reaction. All right, I'm going to do a sample question quickly, There are some others on Orville. I didn't do import all of them here, but there are others that you can practice. And next tutorial will also have additional questions for you to practice. So here you're asked to draw the structures of the missing compounds A to C. It's a typical exam type question. And so already you should figure out that B is the formation of your ylid, and A would have to be an alkyl halide. And so we need to now look at our alkene and our reagents to figure out what the alkyl halide will be. So when we add HBr across a carbon bond, which rule do we normally follow? Or based on the reagents presented, which rule is being employed here? Very good, anti-Markovnikov rule. And so the anti-Markovnikov product will produce the alkyl halide, in which we have the hydrogen being added on carbon number 2 and the bromine being added on carbon number 1. And that alkyl halide would be A. We react that alkyl halide with the phenylphosphine to give us our ylid. And now we are going to react our ylid to give us our alkene C. So let's go through this question. So here we have our anti-Markovnikov addition of HBr. We end up with our alkyl halide, one more propane, and we react our alkyl halide with triphenylphosphine, and they will give us our phosphonium salt. So we have basically substituted the bromine with the phosphorus as we did before, and so now we have our phosphonium salt. We use the base to abstract the proton. So the base is going to remove that proton, and that will generate our ylid. And so now we have the reaction of our ylid with cyclopentanone, the ketone, and that will give us our carbon-carbon double bond. So Wittig reaction takes place with our ylid, and we form our product. The double bond is being formed between the carbon of the carbonyl and the carbon from the ylid. So as I mentioned before, your upcoming tutorial for organic chemistry will include some additional examples so you can get some practice. Okay? Are there questions before we move on? No question? Are we clear? There is an additional CH2 in C. So if you look at your ylid, it has one. Let me go back to the pointer. Your ylid has 1, 2, 3 carbons. One, 2, 3 carbon. Yes, yes, you are correct. You guys are sharp. You guys are sharp. Yes. Okay. Yes, an extra, and this goes back to something I should have mentioned before. Whenever we are doing reaction mechanisms, it's always a good idea to number your carbons so that you are able to track the bonds that are being formed and to make sure that you have the correct number of carbons. So yes, lecturers make mistakes, the same mistakes that you make sometimes. Okay, great. So are we clear on the mechanism same for VITIC, because this is normally a challenging mechanism. It's unusual. It's not what we're used to. Are there any other questions with the VITIC reaction? As I mentioned, there's some more examples on Orvally with the lecture notes that Dr. Brown has posted, and as well as the video, the YouTube video that she has created. Let me thank her, because these slides were created by her. So we're really grateful. Okay, so let's move on to the last topic that we'll look at in carbonyl chemistry, and that is how we can use carbonyls as nucleophiles. So up to this point, all the reactions that we have looked at reactions in which carbonyls react to nucleophiles. So the carbonyls undergo nucleophilic addition reactions. So far, all the reactions that we have seen, the reactions of carbonyls normally involve a nucleophile. However, the carbonyls themselves can become nucleophiles. I'm going to look at that today. That under basic conditions, the carbonyls themselves can become nucleophiles. And when they become nucleophiles, they can undergo similar reactions to what we have seen before with other nucleophilic addition reactions. So we're going to look at ketoenol, which we saw previously, catamerization that before. We look at the formation of enolate anions, alkylation. The final thing we look at is the aldol reaction. So we mentioned before that all the nucleophilic reactions that we have looked at so far are with alkyl halides. So we looked at SN1 and SN2. And with carbonyls, we looked at addition of nucleophiles. And in all cases, the nucleophile is attacking an electron deficient center. However, under some circumstances, certain circumstances, the alpha carbon, that is a carbon which is directly next door to the carbonyl, can also be converted to a nucleophile. So if we look at these three examples, you'll see that for acetone or propanone, the carbon number 2 is our carbonyl. And the carbons which are directly attached to the carbonyl, those carbons are called alpha carbons. So we're using the Greek alphabet, alpha, beta, gamma, etc. So here we have 2 alpha carbons. Here we have 1 alpha carbon and a beta carbon. We have a cyclic ketone. We have 2 alpha carbons and 2 beta carbons. So the carbon which is directly attached to the carbonyl carbon, those are referred to, are noted as alpha carbons. And as you go along the chain, we have alpha, we have beta, and if you have another carbon, the gamma, delta, etc. So we use the Greek alphabet to identify or to label the carbons attached to the carbonyl. Okay. So why is it that they are nucleophilic? If we look at the structure here, we know that oxygen is highly withdrawing, and so we are showing a movement of electrons. So electrons are being pulled towards the oxygen. When that happens, it makes the protons directly attached to the carbon next to the carbonyl. These protons can be removed by a strong base. They're acidic. So the carbon is a positive, and because of inductive effect, the oxygen is electron withdrawing, it pulls electron away from the carbon. The carbon, the 2 carbons that are directly attached to the carbonyl carbon, these protons are acidic. That means because of a strong base, those protons can be removed. So it means, therefore, if we can remove the proton, then what we will form is a nucleophile. And if you do a comparison between, for example, the other functional groups, for example, alkanes and alkenes, we see that the pKa is more acidic than alkenes and alkenes, and less acidic than water and alcohol. So there is some acidity. Because there are weak acids, it requires a strong base to remove these protons. So the base will abstract any of these four, which are labeled in blue. They're all in the alpha position. The base could remove any of these four. The base will remove the proton, the electrons will come in, and so the carbon now becomes negative. This special kind of nucleophile is called a carbanion. So we have looked at carbocation, where the carbon is positively charged. Now we have a carbon which is negatively charged, and this is called a carbanion. So note, it is only the alpha carbons or the hydrogens on the alpha carbons that can be pulled by the base. It is only the protons which are on the alpha carbons, that is the ones directly attached to the carbonyl, which can be pulled by the base. Go ahead, Shanae.
Okay, Miss. Could this happen? Well, maybe not. But so the base extracts the proton, and the electrons from the proton would form a double bond with the carbon and the carbonyl, and then the electrons from the carbonyl would go to the oxygen.
Yes, that is. So you're saying. So this is what you're suggesting. Where did I put my marker? You're suggesting. Let me see what you're suggesting. Are you suggesting the electrons could go here? Where did I put my pointer? Let me. Is that what you're suggesting?
Yes, Miss.
You are very much so correct. That's a resonance form of the carbanion. It's an enolate. So that is a resonance form. So the resonance form, let me see if I can. Your hand is up again, Shanae. So I'm going to use R. I'm going to use R for the alkyl groups that are attached presently. So what you'll have is R, and then you'll have double bond. So that's enolate. So that is a resonance form. You are correct. Okay. So once we have formed the carbanion, this now becomes a nucleophile. Right? And the bases that we normally use strong bases that I mentioned before. So you can use ethoxide or tertiary ethoxide. And these bases you have been exposed to before when we looked at SN1, SN2 reactions. So these are elimination reactions. So these are not foreign to you. We have looked at these bases before. So either of these two strong bases can be used to remove any of these acidic protons. So, which is on the next slide, the enolate, as you preempted me. Wonderful. So this carbanion can now become a nucleophile. So we have created a nucleophile from a carbonyl. And we have been learning so far that carbonyls undergo we could do addition reaction, which means that this nucleophile could actually react to carbonyl. And so we're going to look at those kind of reactions. So this reaction normally occurs on the basic condition, as we mentioned, and the carbon ion can undergo resonance to form an enolate. And enolate refers to enol, OH, or carbon oxygen here, and the ene refers to the carbon-carbon double bond. This is the resonance form of the carbon ion. So the question you're asking, yes, can the enolate work? Yes, it can. Yes, it can. Okay, so we're going to look at how we can now use these carbonyl compounds as nucleophiles. Here we have 3 examples of carbonyl compound: a ketone, aldehyde, and a cyclic ketone. The ketone, which is acetone, has two alpha carbons, so the carbon ion can be on either carbon. And so a reaction can occur between your carbon ion and your alkyl halide. So it can undergo substitution reactions that normal SN1, SN2 reaction you're exposed to before. The reaction can proceed in the exact same way. This becomes our nucleophile, and we are substituting with the bromine. Similarly, here, our alpha carbon, position 2, negative charge will be generated here, and this is able to replace the chlorine. Again, we can treat our carbon ion here as a nucleophile, and it can react with the ketone, as we saw in previous examples. Oh, you're not seeing my pointer. My apologies. Let me go again. So acetone or propanone has 2 alpha carbons. So the carbon ion can be found on either of the carbons. It acts as a nucleophile, and we can have substitution reaction with the bromine. Similarly, here in aldehyde, propanal, or carbon that are attached to the carbon is our alpha carbon. So we'll form a carbon ion here. And again, it can act as a nucleophile and substitute for the chlorine. For cyclic ketone, again, there are 2 possible carbons in which we can form the carbon ion. Again, it can act as a nucleophile, attack a carbonyl, and we have the formation of our alcohol. So when carbonyls form nucleophiles, they react in the same way as other nucleophiles. Okay, so we're going to look at some examples. Here we have acetone, and there are 2 possible positions in which we can treat a carbon ion. And so we can have a reaction between this carbon and so we are adding or substituting to the ethyl propyl bromide, but we also have another alpha carbon, and so the reaction can occur twice, which is why we now have 2 of the alkyl halides added to the acetone. Similarly, we have 2 alpha carbons here, which means that we can generate 2 carbon ions or positions negative on both carbons. And so in excess of your ketone, the reaction can occur twice. So look at some examples. So here we have our ketone, we have acetone, And we have drawn out the carbon to show all of the alpha protons are, so we can see how the base abstracts the proton and the electrons go in to the carbon, generating our carbon ion. This now becomes a nucleophile. The nucleophile, as we saw before, can substitute with the bromine in the alkyl halide. So the mechanism is exactly what we have studied before. Only difference is that we're using the carbon ion as our nucleophile. So it will perform an SN2 reaction as if we had used hydroxide or if we had used cyanide, the same reaction mechanism. And so what we have done basically is extended the carbon chain for the ketone. So we have moved from a ketone that had 3 carbons, we have extended the carbon chain, and the ketone now has 4 carbons. This reaction is known as alkylation because you're adding or you're extending the alkyl chain. So the first step is to generate our carbon ion, which becomes our nucleophile. The nucleophile attacks the alkyl halide like any other nucleophile that we have seen before, and we have extended the carbon chain. And so this reaction is called or known as an alkylation reaction. So in order to reduce the side reactions between the base and the alkyl halide, because if you have a base with an alkyl halide, the base can also be a nucleophile. And so what we normally do is use bulkier bases instead of hydroxide. So we use ethoxide, tertiary methoxide, and so on. And that will generate our carbon ion. This now becomes our nucleophile, and it performs a substitution reaction and extends the carbon chain on alkylation. Are there any questions? Are there any questions with this mechanism? Yes. So to reduce the side reactions, we use larger bases. So we use ethoxide, we use tertiary methoxide, all the bases that we normally use, instead of using hydroxide, for example. Okay. Another reaction that these carbon ions can undergo is the formation of aldols. And as the name suggests, an aldol, an alcohol with a carbonyl group. So if we had a hydrogen here, it would be from an aldehyde. And so we have an aldol reaction. The reaction can also continue, and we can form a carbon double bond. And so the product that we form here in the first step is a beta hydroxy compound, because the hydroxyl group is going to be added in the beta position, that is beta to the carbonyl group. So here we have our alpha positions, and our hydroxyl group will end up in the beta position. So the product that is formed is referred to a beta hydroxy compound. Let's see if we can work through the mechanism. The first step is that we are going to form our carbon ion. So the base will abstract one of the acidic protons, and we end up with our carbon ion. This carbon ion now becomes a nucleophile. And we know that carbonyl compounds are susceptible to nucleophilic addition reactions. So this now becomes our nucleophile. So this is our nucleophile and can now react with our carbonyl compound. So here we have our carbonyl compound. So how would I draw my arrow? Anybody? Volunteers? Okay. So somebody said from oxygen to carbon. That is not correct. From the dots to the center carbon. So remember, it's a nucleophilic addition reaction. This is our nucleophile. We have a carbon ion negative charge here. And so we can easily use that negative charge as our nucleophile. And the reaction will proceed in the exact same way we have seen countless of times with a nucleophile and a carbonyl compound. Okay. So we have the formation of a new bond between our carbon ion and our carbonyl carbon. Is where we are now. And the next step is we will protonate the oxygen and we end up with a hydroxyl group. So notice now the hydroxyl group is added to the beta carbon, meaning beta in relation to your carbonyl group. So we have alpha, beta carbon. So we have formed a beta hydroxy compound. Are there any questions before I proceed? Okay, no question. It means therefore, so the example that I showed previously, we had two different ketones. We had cyclopentanone, and we had acetone. But if the reaction can occur between ketones, it means therefore that the reaction could actually occur between two of the same compound, because one can act as a nucleophile and the other act as a substrate. So here we have acetone again. And we are using a base to remove the acidic proton to form our carbon ion. This carbon ion, which was formed from acetone, could also react with acetone. And so the reaction will occur between two molecules of the same compound. So we have our acetone, which generated our carbon ion, now acting as a nucleophile with acetone. And again, we will form our beta hydroxy compound. So the reaction can occur between two different ketones or carbonyl compounds. Reaction can also occur between two molecules of the same compound. Is that clear to everyone? Are there any questions? Good. So I see in the chat that persons have been asking about reaction occur on both sides. The reaction can occur on both sides if your reagent is in excess. Go ahead. Justin just raise his hand. No question? Okay. The hydroxy compound can undergo a further reaction in which we can have a dehydration. We can lose water. So if we go back to this slide, here we have a hydroxy group.
The mic
Yes,
was
yes, Justin.
I was wondering,
Okay.
even after reacting on both sides, it's still a ketone, right? So,
correct.
So then, if there's even more excess, can it just react with it then? Like it can like attack the ketone So would this reaction like go
You mean
on
attack
forever? If there's like at
no,
least
it won't go on forever because normally we're planning a reaction like this. We would have worked out the stoichiometry to determine what quantity, what moles we need for each of the reactants to get the product that we want.
Okay.
So it would have a planned reaction. All right. Okay. So if you look at the structure, you'll notice that the carbon in beta position has an OH group, and the alpha carbon has 2 protons. It means that we could actually lose water across the alpha and the beta carbon. We could lose water by removing the OH from the beta carbon and the proton from the alpha carbon. Right? So when we remove OH and proton for dehydration, so in the presence of heat, we could actually dehydrate the beta hydroxy compound, and we remove water across the alpha beta carbons. And what we end up forming is an alpha beta unsaturated ketone, meaning a ketone double bond between the alpha and the beta carbons. So once we have formed the hydroxy compound, beta hydroxy compound, in the presence of heat, we can have a dehydration, that is a loss of water, and we have the formation of an alpha beta hydroxy compound. Are we clear? Any questions? We have 4 more minutes to go. Are there any questions? So your next tutorial will have some examples. And as I mentioned before, some additional examples were posted on the YouTube videos that were uploaded by Dr. Brown. You'll also see some examples on the PDF lecture notes that we had before. So all of those are on Orveli. What do you want me to repeat, Shaniska? All right, so remember we have office hours, but my office hours are Tuesdays 3 to 5, Thursdays 10 to 11:55. Dr. Brown has office hours, I think Tuesdays 1 to 3. Is that correct, Dr. Brown? Your office hours? Tuesdays 1 to 3, and I think Fridays 1 to 3, is that correct? Yes, Tuesdays and Fridays 1 to 3. So you can just log on. Again, as I mentioned, the Orveli, we have the lecture notes uploaded. This lecture video is also uploaded. A YouTube video is there. This has been recorded, so this again will be on Blackboard Collaborate, so you are able to review what we did today. So both this lecture on DBC as well as the YouTube videos are available for you to review. Okay. The tutorials have also been recorded. So the tutorial that was done on Monday at 9 was also recorded. If you go into BBC and you look to the left-hand corner, there's an arrow at the top. You can click and it says recorded sessions, and you will see all that we have recorded since we have resumed lectures online. Okay. Again, feel free to email me or Dr. Brown, and one of us, the questions that you may have. So your course test will be from Grignard reagent up to what we have covered today. Okay, so as I always say, practice, practice, practice. That's the only way we can learn reaction mechanisms. Practicing pushing our arrows, recognizing what's a nucleophile, electrophile, taking notes at the direction of our arrows, the correct type of arrow, that we use. And once we do that, you are fine. In a few days, you'll get an email information about your course test. Yes, lecture recordings will be on Orvally until the end of the semester. So in a couple of days' time, you should see some information about the date, time, and format of your course test number 2. And we'll try to structure the course test so that you can have an idea what your final exam will look like. So we'll try to use a similar format to prepare you for your final exam. The course test is from Grignard to today's lecture. Okay, have a good day, everyone. Feel free to contact us if you have additional questions. Okay, bye.